Welcome to I Can Science That. Lately we've been sciencing the relationship between momentum and kinetic energy. Today we'll take a look at levers. There is perhaps no better way to illustrate the definition of work than the simple lever. That's right, we'll show that levers conserve kinetic energy. And in so doing, we'll explain why energy equals force times distance. Levers and other simple machines are everywhere. They allow us to massively multiply the amount of force we can apply. But if we're multiplying force, how can energy be conserved? Let's start with a review of mechanical advantage. This is one of those videos that's going to be almost entirely math. This video, while it is all math, is not going to go beyond just your basic algebra. So I want to encourage everyone, even if you're not that comfortable with it, to simply follow along. I'm confident that if you apply yourself, you can follow all the steps that I am going to show here and make sure I haven't been trying to pull a fast one on you or anything like that. Mechanical advantage is a concept we learn in our physics classes pretty early on. And it goes something like this. When we have a lever, we'll have what we call a fulcrum, which is a pivot point, and then moment arms. Arms are some sort of beam, which we'll assume to be perfectly rigid, that extends to either side of this rotating pivot. We'll apply a force to one end of the beam, and the force will cause this end to come down, rotating around this point, which will cause this end to go up. And the mechanical advantage we get is that if these arm lengths are different, we'll get a different amount of force than we put in. The penalty that we pay for that is we're also going to get a different amount of distance. So just looking at the basic geometry here, we can see that if this distance is R1 and this distance is R2, we can construct little triangles to show the motion of what we did here. This being R2, this being the distance D2, like the displacement. How far down did we push this end of the triangle? And we can see that this triangle and this triangle are similar. And you may remember the ratio rule from similar triangles. Simply that we can say now that however far we pushed this end will move according to the same ratio as the moment arm ratios. The other thing from the mechanical advantage was that when you push it very far on this end, and you get a small displacement on this end, what you're going to get is a big boost in the amount of force. So if this arm here, R1, is smaller than this one, R2, we'll get an increase in the amount of force and a decrease in the amount of distance. So here's that ratio here. We have the distance ratio equals the same as the moment arm lengths, and the force ratio is just the inverse, just the opposite. We can call this simple relationship the mechanical advantage equation, and we probably want to rearrange it like this. With a simple cross multiply, we can say that the force we put in times the displacement we put in is going to be equal to the force we get out times the displacement that we get out. So if we want to increase the force on the other end, we're going to get much less distance than we put in. We're going to have to put in extra distance if we want to get extra force on the outside. And that's exactly how the jack works when you're trying to jack up a car. You have to pump it a whole lot of times to get the car to move a few inches. Now you might remember a few videos back, we introduced the definition of work. And we said in the simple form that work was simply force times distance. And well, that's what we have right here. We're saying that the work on the one side is equal to the work on the other side. The work that you put in is equal to the work that you get out. And that right there really probably should be the starting point of our definition of work. What better explanation for conservation of energy and this force times distance definition of work than the simple lever? We can do experiments with levers in the classroom. We're all comfortable with levers. We know that jacks work. Really, all we're saying is that work, the force times the distance, has been conserved on either end of our lever. Steve Mould has a video on levers that is really quite interesting. Let's take a brief look at that.
Now this end of this lever is traveling twice as fast as this end of this lever because it's twice as far from the pivot. So after the engines turn off, the half kilogram mass will be traveling at twice the speed of the 1 kilogram mass. So how does that affect its kinetic energy?
In Steve's example, he imagines a rocket on one end of a lever. He imagines the rocket applies a steady 1 Newton of force on the one end of the lever. In his thought experiment, we're going to imagine that the lever arm here, I'm calling R2, is exactly twice the length of R1. And from that, we can conclude that the displacement we're going to get out on the other end is exactly twice the displacement that the rocket is moving through. Now, if the displacements have this linear relationship, we can infer that the velocities have that same relationship. If the rocket builds up some speed as a result of this 1 Newton of force that it's applying, the speed on this end and the speed coming out on the other end are given with this. Like the speed coming out on the right-hand side here is going to be twice whatever speed the rocket is going on the left-hand side. And just so we don't get confused about a later example, I'm going to explain. I am saying that the rocket starts from rest, and then we fire up that 1 Newton thrust, and it builds up to V1. So the rocket is going to build from 0 to V1 speed, and this being a rigid bar, the bar moving for some fixed amount of time. In that amount of time, this end moves D2, this end moves D1 in the same time, meaning if this side is at V1, this side is now at 2 V1. Continuing ahead with Steve Mould's thought experiment, we're going to put a mass on the other end of the lever. Remember, the rockets are set up to apply exactly 1 Newton of force, and in the thought experiment, we're going to allow the rocket side to move exactly 1 meter. Based on mechanical advantage, if we have 1 Newton of force being applied here, with a 2-to-1 moment arm, we'll get a half a Newton on this end. In this example, we have equal moment arms, and so we'll get 1 Newton on this end. With that in mind, and thinking ahead to F equals ma, we want to get the exact same amount of acceleration in both cases, and so we'll put half the mass on this end that we put on this end. 1 Newton being applied to a 1 kilogram mass should generate the same amount of acceleration as half a Newton applied to a half a kilogram of mass on this side. And Steve posits that based on that, these two scenarios should be the same. Spoiler alert, they're not, and that's what his video is all about. In Steve Mould's video, he goes on to build a physical experiment that demonstrates that these are, in fact, different and that they feel different and behave differently. But he doesn't show the math of exactly why. So that's what I'm going to do in this video, is I'm going to go through the math and show exactly where the difference occurs when it is not at first obvious that these two scenarios will be different. Continuing with the thought experiment, if we apply a 1 Newton force to the bottom of our lever, we'll come up with some velocity. Some acceleration occurs and we'll end up with a velocity. Let's call that velocity v. The 2-to-1 moment arm ratio says that if we have 1v on this end, we'll have 2v on the other end. On the other side, we're applying our 1 Newton force again, and we're going to have it move over 1 meter. And our intuition tells us that, sure, we're going to get 1v here again. So if we're going to get 1v on this end, what do we get on the other side? Well, the moment arms are equal, so that means in this case, we have 1v and 1v, whereas in this case, we had 1v and 2v. Now, right away, looking at this at a glance, we're starting to see conservation of momentum. I think conservation of momentum would be a natural inclination for what we're looking at. We have mass times velocity, and 1 times 1, and 2 velocity times 1/2 mass is, again, the same amount of mass times velocity. That looks like conservation of momentum. It is not. Let me stress again, in Steve Mould's video, he goes on to show with a physical demonstration that this is incorrect. What I'm showing you is wrong, and we're going to use conservation of energy to show that it's wrong and explain where we made the mistake. So do not allow yourself to jump to the conclusion that we have conserved momentum. Taking a look at the energy equation. The kinetic energy equation is 1/2 mass times velocity squared. What is that? In our left-hand case, our mass is 1/2 kilogram. We'll put that in, and our velocity is 2v. We'll put that in. If we multiply that out, we get 1/2 times 1/2 times 2 squared times v squared, or just v squared. The kinetic energy on this side is v squared. What about on the other side? On the other side, we have a 1 kilogram mass moving at 1v. So we plug those in, and we just get 1/2 v squared. So taking a look right away, I think you'll notice that the kinetic energy does not match. That should give you pause. We put in 1 Newton on either side, same amount of force, and we said we were going to allow it to move over 1 meter on both sides. And so that should have been the same amount of energy put into the system on both sides, but we got different energies out on both sides. I will remind you, first of all, that we did not use that 1 meter of distance that we promised. It didn't come into the equation anywhere. And that should give you an indication that something hasn't balanced. We haven't been careful about something. We've made an assumption somewhere. So let's all pause the video here and put in a comment, where do you think I have made an assumption that was incorrect? Something doesn't add up. Did I make an error with the math? Can you find it? Or did I assume something that isn't correct? Pause the video here and we'll be back in 3, 2, 1, and we're back. Those kinetic energies, I said were going to be the same. We're going to apply 1 Newton for 1 meter. We should have 1 Newton meter however you slice it. The only way for those kinetic energies to be the same is if this velocity and that velocity are not the same. There's no way for v squared to be equal to 1/2 v squared. These two v's must be different. And in fact, if you watch the Steve Mould's video, that is exactly his conclusion, and he concludes it and demonstrates it with a physical demonstration. What Steve Mould did not do is show the math of exactly why that's wrong. So I would like to do that now. Let's do the math and figure out exactly what is the V here on the left side, what is the V on the right side, and see if we can't shed a little light on this mystery. There are a couple of ways to approach this problem, and I think probably the most obvious one is to continue with this energy analysis. If we take the kinetic energy equation, the 1/2 mv squared should be the energy we get out of the system. And the energy that we put into the system was, of course, force times distance. So we said that was 1 Newton acting over 1 meter. So these two kinetic energies have to be equal. We can alternatively write a Newton as a kilogram meter per second squared. So that tells us that our input energy is 1 kilogram meter squared per second squared. That's a Newton times a meter. Our output energy is going to be in this form. So it's 1/2 times 1/2 kilogram, or 1/4 kilogram, times the V2 squared. So I've got that on there. And we're trying to solve for velocity. We want to know what is the velocity. So let's just solve this. The kilograms cancel. And so we are left with V2 squared is 4 meters squared per second squared. So we'll square root both sides, and there's your solution. V2, the velocity at that point, is 2 meters per second. And based on our moment arm of 2-to-1 ratio, that means V1, the velocity down here, is 1 meter per second. So there you go. We have solved using the energy approach the velocity on the left side. Let's do the same thing for the right-hand side. We have the same 1 Newton meter input, and this time we have 1 kilogram of mass. So 1/2 times our kilogram times V2 squared. Again, our kilograms cancel. We have 1 meter squared per second squared equals 1/2 V2 squared. Or V2 squared is 2 meters squared per second squared. Square root both sides. And V2 is the square root of 2 meters per second. With our moment arms being equal in this case, that means V1 is also square root of 2 meters per second. And there's your answer. As predicted, the energy approach tells us that the velocities that we get where our rocket is pushing on the lever are not equal. This is, the square root of 2, which is approximately, 1.4. It's like 1.4 meters per second on this side, whereas on this side, we get 1. So this rocket is moving about 40% faster than this rocket, even though they applied the same force over the same distance. Back when we introduced this thought experiment, our intuition told us that the velocities should be the same. So maybe this is telling us that this energy approach is incorrect. Maybe this whole energy thing is wrong, and this is proof that the energy thing is wrong. Let's approach this then in a different way. Let's take the force approach, where we'll start from the equation force equals mass times acceleration. We'll use that to calculate the acceleration and from there work out what the final velocity is. So based on our lever arm and our mechanical advantage, we know that if we apply 1 Newton of force on this end, we're going to get 1/2 Newton of force on that end. If we have 1/2 Newton of force applied to a 1/2 kilogram mass, our force, here's our 1 Newton, times our 1/2 kilogram, times our final acceleration. We can solve that for our acceleration. The 1/2s cancel, the kilograms cancel, and we get our acceleration is 1 meter per second squared. So that's our acceleration. How do we go from acceleration to velocity? Well, velocity is just going to be acceleration times time. Well, we need time. So where are we going to get time? Let me propose we can get time from this relationship. If we know the distance that the object moved, distance is 1/2 acceleration times time squared. So we know the distance. The distance we said was 1 meter here, and the moment arm gives us 2 meters up here. So that's the 1/2 times our acceleration. Our acceleration is 1 meter per second squared, and then times t squared. Let's solve that for t. We're going to get the m's, the meters cancel, and the 2 comes over to be 4, and we can take the second squared over to the other side. T squared is 4 seconds squared. So let's square root both sides. And we find that T equals 2 seconds. It takes 2 seconds applying 1 Newton to get that mass going. And if we are accelerating at 1 meter per second squared for 2 seconds, the velocity is 2 meters per second at that end. Using our moment-arm relationship, that means we have 1 meter per second at this end. So now we have the velocity on this version. Let's do the same thing for the equal moment arms. Okay, we're over here now. We're going to do the exact same thing. We have 1 Newton this time. We have equal moment arms, so we have equal forces. 1 Newton, 1 kilogram. The acceleration there is pretty easy. That is going to be 1 meter per second squared. Doing the same thing, distance. Now the distance here was 1 meter, and so that'll be 1 meter up here. 1 meter equals 1 meter per second squared times the 1/2 times t squared. And we'll solve that for t again, and this time t is the square root of 2 seconds. If we apply 1 meter per second squared for the square root of t seconds, we end up with square root of 2 meters per second. That is the speed at this end, and because of equal moment arms, it is also the speed at that end. So let's recap. What did we just find? Using either approach, we got the exact same results. Those results are that even though we use the exact same force in both cases, and we applied that force over the exact same distance, the velocities that we get are different. The only way we can resolve that, the only way that can be true, is if we applied that same Newton for different amounts of time towards different masses. And that's exactly what we've done. We've applied our energy to different masses, resulting in the same total kinetic energy by applying that force for different amounts of time. And for those who are skeptical of math and are inclined to say that just proves that this math is all wrong, that this is some sort of mathematical sham that I'm trying to pull on you here, that none of this matters without a physical demonstration, that the video I've been referring to, Steve Mould's video, has the physical demonstration in it. And in Steve Mould's thought experiment, it began with a hasty, intuitive conclusion that was incorrect. The intuitive conclusion was that these velocities would be the same when the math shows that it is not. The actual laws of physics show that it is not. And indeed, when you do the actual experiment in real life, you find out that those velocities are not the same. As I first started researching this topic, I watched Steve Mould's video and I was asking myself, why is that though? But why, right? And I eventually came to the results that I've just shared with you. I started with this simple diagram of a lever, right? With a fulcrum and some moment arms, and you apply a force on one side and you have like a mass on the other side. Where do we actually get this mechanical advantage equation? I mean, we can show it empirically. It's very simple to show empirically, but can we prove it? Can we derive it from some more basic principles? And as I was perusing, looking for other discussions of the Steve Mould video, I found one particular post on Reddit that simply said these 3 words, free body diagram. So I thought, of course, free body diagram. Let's do a free body diagram. And for those of you who haven't done a free body diagram before, we're just going to say, isolate your picture to a single object. Show one object, and it's going to be free. It's just floating in space with forces acting on it that we have to mark and label on the diagram. So the lever itself, this beam, this assumed to be rigid beam, is our free body. And I know that I'm applying a force on the one end of my lever. So if the free body is not accelerating, and it is not, has no angular acceleration, has no linear acceleration, then all the forces acting on it must balance perfectly. And we can use our free body diagram to count up what all the forces must be to make that happen. So we know that I'm applying a force on the one end, and I put a mass on the other end. So that mass is applying some force on the other end of the lever. So now I see that there are forces pushing the beam down. If it is a free body and is not accelerating, there must be an equal force pushing upwards. And that's coming from the fulcrum. The fulcrum is pushing up, and the two other forces are pushing down, and those must add up. They must add and be equal so that there's no acceleration on my beam. Well, that's pretty straightforward. The other thing is that I don't want any rotation. I don't want rotational acceleration. And that means there must be no torque, zero net torque acting on the beam. To keep things simple, let's work around the fulcrum. F3 applies zero torque at the point of the fulcrum, so we can drop that one out. And we can say that F2 is trying to rotate the beam clockwise. F1 is trying to rotate the beam counterclockwise. So if the beam is not rotating, those torques must be equal. And the equation of torque is force times the moment arm. So that tells us that if there is no torque, no net torque on this beam, that F1 times R1 must equal F2 times R2. And that, from the free body diagram, is literally the derivation of our mechanical advantage. So there you go. That is why work must be defined as force times distance. That is why we use work as our unit of energy. That is why levers must conserve energy. But you ask, what about momentum? What about conservation of momentum? Isn't that a thing? Let's imagine a different scenario. I'm thinking of a rocket, and in this case, instead of applying a steady force on the rocket, I'm going to give the rocket some speed and let it smack into the beam. It's cruising along at velocity v1, and it slams into the beam, and that beam brings the rocket to rest. And in so doing, it flings a mass here on the other side, and boom, it shoots that mass off the other way. Can we look at this as a case of conservation of momentum? Let's take a look at the momentum. The rocket's momentum was pointed down when we started, and all that momentum is transferred somewhere. The mass's momentum starts at zero, but that ends up going upwards. So that's not a conservation of momentum. That's a reversal of momentum. We took momentum that started going down and ended up with momentum going up. That momentum has been reflected. That's not been conserved. Of course, conservation of momentum is a law, and momentum must be conserved. What does it tell us? If we remember back to the law of conservation of momentum, and what did we say? What was the nuance of it? It was that in a closed system, momentum must be conserved in the absence of a net external force. In our previous diagram, we did in fact have a net external force. The net external force was acting upwards from the fulcrum. So what are we seeing here? What are we not counting? Is that the momentum of the rocket is being transferred down through the fulcrum. And this momentum upwards to the mass is coming from that fulcrum. The fulcrum is what is pushing up in both cases. It is pushing against the rocket and absorbing that downward momentum, and then again pushing up on the mass and absorbing again that momentum. So this is not a case of momentum being conserved between the rocket and the mass. They are both transferring momentum through the fulcrum to whatever the fulcrum is mounted on, presumably the Earth. If you were paying close attention, you know that I've been playing a little fast and loose with my use of the word velocity. Up through this presentation, I've been referring to the letter V and calling it velocity when really I have meant speed. I have meant the magnitude of velocity up until now. And now suddenly I'm changing things. I'm insisting that velocity has a direction here in my momentum discussion, whereas in my kinetic energy discussion, I was perfectly willing to simply refer to velocity as only the speed with no direction. The explanation for that is that momentum is a vector quantity. Momentum has direction, whereas with energy, there is no direction. Kinetic energy does not have direction. It is not a vector quantity. It's what we call a scalar quantity. So based on that, I have been simply referring to what should truly be called speed in all of these equations up until now as the word velocity. Sometimes we say velocity, like kinetic energy is mass times velocity squared, when really you can't square a vector quantity. That would be a vector dotted with itself, which is the magnitude of the vector squared. We just, for shorthand, always simply call that velocity, but really we do mean a directionless quantity that is just the magnitude of the velocity. But that matters when you're starting to talk about momentum. Consider the equation that we've been working with. Because we assumed this bar was perfectly rigid, and that gave us this equation. And this equation holds at any velocity. What does that mean? It means as the rocket's velocity, v1, increases, the v2 also increases. But what we had imagined in our heads was a situation where the velocity v1 starts high, but then gets smaller. It slows down. But in the same time, this v2 increases. And that is not what our equation is here. The momentum isn't being transferred this way. In fact, this equation that we had doesn't even have mass in it. Momentum is mass times velocity, and there's no mass in this equation. It doesn't matter what the masses are. If we have this rigid beam, we have to have this equation. But wait, hold up there, Mr. I can science that. What about these? These are clearly transferring momentum from one body to another. Yes, they are. But watch how the teeterboard flexes. This is not a rigid beam. This is an example of a spring. One side absorbs the energy and transfers it to the other side. And just like with the other springs that we saw before, it is energy that is being conserved. So let's sum it up. What have we learned today? The mechanical advantage equation, force times distance. The force that you put in times the distance that you put in is equal to the force you get out times the distance you get out. Meaning, if you want extra force on the output, you're going to have to put extra distance into the input. And this is going to be the same for all of these so-called simple machines like levers, pulleys, gears, etc. That's the same equation as that energy-work relationship. That energy is force times distance. And based on that, I'm willing to say that, of course, energy is being conserved by a lever, just like it is with a spring or any of these other things that we've been investigating. But I'm willing to say that I think levers are probably the very best way to show that this work equation, energy is force times distance, is a meaningful quantity, and it is like the fundamental quantity that we're experiencing when we use any of these simple machines. We showed that a free body diagram, we can use that to derive this equation. We don't have to simply assume it. We don't have to simply guess it. We don't even have to measure it in the lab. We can, of course, measure it in the lab. And we've done that many times. We can all do that in our own homes. We also saw that we can work the problem in different ways, but no matter how we approach it, we're always going to get this same answer. We're going to get it if we take an energy approach and we start with kinetic energy equals force times distance. We're going to get the exact same results as if we take a force equals mass times acceleration approach. And the reason that works and the fact that that works gives us confidence that we're dealing with actual physical laws, because the laws of nature, if they're correct, they must agree with each other. And I think that pretty much sums up the question of kinetic energy, where it comes from, what it means, and whether or not force times distance is a meaningful quantity. If nothing else, I think we've clearly showed that levers, at least, and by extension, any other of these simple mechanical tools that follow the mechanical advantage formula, conserve force times distance.